All right, so today we're going to be doing Lecture 7, Continuity. So we say that a function is continuous only if it can be drawn without lifting your pencil from the paper. If you have to lift your pencil from the paper to draw the graph, it is called discontinuous. So continuous and discontinuous are opposites. It's a continuous function if you can draw it without lifting your pencil from the paper. So what I'm going to do is I'm going to go ahead and draw you a line right here. And it would probably help if I actually plugged in my tablet. So hold on just a second. Okay. So when you have a continuous function, you can draw it without lifting your pencil from the paper. So an example of a continuous function would be something like this. I draw the line, it goes in this direction infinitely, and it goes in this direction infinitely. And I can draw this line without lifting my pencil from the paper. So because I can do that, we say that this graph is continuous, and the function is also continuous. An example of a discontinuous function would be something like this. So I'm drawing my line, and then I lift my pencil up from the paper, and then I put it back down. And I keep on drawing the line, infinitely in this direction, and infinitely in this direction. So because I had to lift my pencil from the paper, we say that this is discontinuous, okay? So functions, all functions are either going to be continuous, or they're going to be discontinuous. And if you have any gaps in the domain or any gaps in the range, we say that it's discontinuous, right? There's actually also a third option. A function could also be what's called absolutely continuous. Absolutely continuous. So I posted a video in the module, and it's about the Cantor function. Now, the Cantor function is really strange because it's one of those examples of a function that is continuous, but it's not absolutely continuous. So that would be a great video to watch, and it's on the Cantor function. But all of that aside, you really just need to know whether a function is continuous or discontinuous, okay? So down here, I have an example of a parabola that I graphed. You could say that this function is y equals x squared. Y equals x squared. That's the quadratic function. And when you graph it, you know, there's no gaps in the domain. You can draw this graph without lifting your pencil from the paper. So this would be a continuous graph. But if I was to put a gap in the domain and lift up my pencil from the paper, then that would be called discontinuous. And the point where I lift my pencil off of the paper is called the point of discontinuity. The point of discontinuity. Okay? So that's important to know too. The point is called the point of discontinuity. So over here on this graph, I have two graphs. I have a blue graph and I have a red graph. Notice that the red graph is continuous because I can draw the red graph without lifting my pencil from the paper. But the blue graph is not continuous. It's actually discontinuous. And why is that? It's because when I draw the graph and I get to this point, the graph has a gap in the range, right? I start down here and then I jump all the way up to here. And then the function keeps on going in this direction. So this would be the point of discontinuity right here. That's where the disconnect happens. So that's why the blue function is discontinuous while the red function is continuous. All right. Now, we're going to talk about three types of discontinuities today. There is the removable discontinuity, the jump discontinuity, and the infinite discontinuity. And I made a couple videos over the week that explain continuity in a really short way. So some of these videos are shorter than 5 minutes, but if you do get a chance, go ahead and watch those. Okay? So let's talk about all three different types of discontinuities. Okay, so the first type of discontinuity is the removable discontinuity. These graphs have at least one point that is removed from the graph, thus leaving a hole in the graph. Okay? Now, when you have a removable discontinuity, it's important to understand that the two ends of a function will meet at some point if there's a removable discontinuity. So down here, I have this graph where it kind of looks like a parabola shape until you get to this point and then it's linear. So there's a hole right there in the graph. You see that? There's a hole right here. And the reason why is it's because I removed a point. I took the point out from right here and I put it all the way down here. So there's a hole in the graph. That means that this function cannot be continuous, right? It would be discontinuous because it has a discontinuity right here where this hole is. So the two ends of the function do meet, but the point has been taken out, right? So that would be called a removable discontinuity. Now, when do these occur in practice? Well, sometimes when you're graphing, let's say rational expressions, if you're ever graphing a rational expression, you know that there's a numerator and a denominator and a fraction, right? Everybody knows that. The numerator is the top of the fraction and the denominator is the bottom of the fraction. Well, sometimes you can factor the top and the bottom and then cancel out factors, right? Because if it's the same factor on the top and bottom, then you can pretty much cancel them out. So I'm going to do a little example over here. Let's say you have this rational expression and you factor it, and it has the factors x plus 2, x minus 1 on the top of the fraction. And then on the bottom of the fraction, you have, let's say, x minus 1, right? You know that there's a top to this fraction, and you know that there's a bottom to this fraction. Now, if something is the same on the top and bottom, like I said earlier, you can cross them out, and then your answer would just be whatever you have left, which would be x plus 2 in this case. So what you can do is you can actually graph this, and you can also graph this up here. And what you'll notice is this missing factor right here, this missing factor, this x minus 1 that we crossed out, that's going to have the removable discontinuity. So if you were to solve this for x, you would get x equals positive 1. And this is where the removable discontinuity would be. Okay? So that's the removable discontinuity. You can take a point out of a graph and you're going to be left with a hole in the graph. Okay? Now, think about this. You can also make a discontinuous function continuous again, right? You could do that by filling in the hole, right? So I could pick up this point right here and I could put it in this hole and then kind of like this, and then the function would be continuous again, right? I wouldn't have to lift up my pencil right here just to do the hole. So when you have a removable discontinuity, you're pretty much going to have a hole in the graph. And that's what it means to be a removable discontinuity. All right. Now, there's another type of discontinuity called a jump discontinuity. It seems similar, but it's actually totally different from the last one. So a jump discontinuity is when you have graphs that jump. That's pretty self-explainable, right? Down here, see how the function jumps up? Once it gets to this point, it jumps up and then it keeps on going in this direction. And if you look right here at this graph in the middle, you'll notice that the function is going on and on like this to the right. And then once you get to x equals 0, the function jumps up to y equals 1, and then it keeps on going in this direction. So a jump discontinuity is when you're going to have a graph that jumps, and it's going to leave a gap in the range, all the y values, right? There are y values that this function never takes up because there's a gap in the range. And when you have a jump discontinuity, this is what really sets it apart from a removable discontinuity. The two ends of the graph will not meet. The two ends of the graph will not meet when there's a jump discontinuity. So if you look over here at this picture to the right, you'll notice that this function has a gap in the range, right? It starts up here, and then at some point it drops, it jumps down to this point, and then it keeps on going in this direction again, right? There's a gap in the range. The graph has a jump discontinuity right here. And you'll notice that the two ends of the graph will not meet when you have a jump discontinuity. That's totally different, right? Because when we were talking about removable discontinuities back here, we have the two ends of the function actually meeting together. But when you do a jump discontinuity, the two ends of the graph will never meet, okay? Because the graph jumps. Now, you could think about it this way. You could take a discontinuous function that has a jump discontinuity, and you can kind of repair it so it becomes a continuous function again, right? So imagine if I took this end of the graph and I just sort of grabbed it and I moved it downwards and I filled up this hole, and then the function would go in this direction again, right? You would have a continuous function at this point, right? Because the hole has been plugged in by that point. So that's what a jump discontinuity is. The graph just jumps, okay? There's no other way to describe it. You'll know it when you see it. So that's called the jump discontinuity. And last but not least, you have the easiest type of discontinuity, the infinite discontinuity. This is any graph that has a vertical asymptote, right? We've been talking about parent functions for the last week, where some of them have horizontal asymptotes and some of them have vertical asymptotes. So when you graph these, when you have that vertical asymptote, the function is going to display asymptotic action, right? It's going to have this point where the graph is, it's approaching some number in the x coordinates and it suddenly shoots up or shoots down. Like this logarithmic function right here, y equals log of x. If you were to graph this, you would see that this function has a vertical asymptote. And by the way, it's going to be at x equals 0. That's the vertical asymptote. All right. So when this function gets closer and closer to the line x equals 0, which is the y-axis, by the way, once the function gets closer and closer to the y-axis, it starts shooting downwards. So we say that it has an infinite discontinuity at x equals 0. So we're always going to use those vertical asymptotes when we do infinite discontinuities. Same thing in the middle, right? Look at this function in the middle. This is y equals 1 over x squared. If you were to graph this, you would notice that this function has a vertical asymptote at x equals 0, right? And that's because if you put 0 in the denominator, you'd be dividing by 0, and that's no good, right? So this function has an infinite discontinuity. Where? At x equals 0, because that's where the vertical asymptote is. And then this function over here on the right side, notice how the function comes in from the left. And once it reaches a certain point, it starts displaying asymptotic behavior. And then the function comes up from the bottom on this side, and then it keeps on going this way because that function has a vertical asymptote right here. So we say that this function has an infinite discontinuity right there. Okay. And the functions that we talked about that were called the parent functions, we talked about logarithms, we talked about the reciprocal functions, and those are the functions that are going to have vertical asymptotes. Exponential functions, those actually have horizontal asymptotes, so we're not really going to talk about those today. But only graphs that have vertical asymptotes have infinite discontinuities. So I think that's the easiest type of discontinuity to remember, because you're always going to have vertical asymptotes. Okay? All right, let's move on to the next slide. So you know the three types of discontinuities now. So now what we're going to do is we're going to sketch these graphs on our paper, and we're going to identify where the discontinuities are and what types there are, right? We can explain their location and what type of discontinuity they are from those three types that we talked about earlier. Okay, so let's look at this first function, number 1 over here. Notice that this function, it kind of meets right here, but it has a hole in the graph. This is called a removable discontinuity because it's got that hole. And the two ends would actually meet if it wasn't for that hole in the graph. So this has a removable discontinuity. Discontinuity. Where? It's at x equals x0 or x naught, as they say. So at that point on the x-axis, we have a discontinuity in the function. Okay? And the reason why I chose removable instead of jump is because the function isn't jumping, it just has a point that's missing, right? That's why it has that hole in the graph. So that's a removable discontinuity. Okay, let's look at the one below it. This one is number 2. So let's talk about this one. What type of discontinuity do you see right here? Is it removable? Is it jump? Or is it infinite? What do you think? If you think you know it, go ahead and put it in the chat box. Is it removable? Is it jump? Or is it infinite? Okay, I'm getting some answers. Yep. All of you are right so far. Jump, 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 jump. Good. This is a jump discontinuity. This is a jump discontinuity. Discontinuity. It's hard to spell. I'm a math teacher, not an English teacher. But this is a jump discontinuity. And why is that? Because when the function gets closer and closer to x0, it jumps in the range, right? There are y values that are not being taken up right here. And then the function keeps on going in this direction again, but just at a different y value, right? At a different height, you could say. So there's a jump discontinuity here at x equals x0. Okay, so you can clearly see the difference between removable and jump. What about number 3 up here? What type of discontinuity do you see up here? And where is it on the x-axis? If you think you know it, go ahead and put it in the chat box. Where is the discontinuity? Where is its location on the x-axis? And what type of discontinuity is it? Is it removable? Is it jump? Or is it infinite? So there's 3 types of discontinuities. Is it removable? Is it jump? Or is it infinite? All right, I'm getting some answers. Yep. It's infinite, right? It's infinite. So we say it has an infinite discontinuity. Discontinuity. And the reason why it's infinite is because it has a what? It has a vertical asymptote right here on the y-axis. So that would be at x equals 0. That would be the y-axis, right? That's that vertical line. So it's going to have a vertical asymptote at x equals 0. That's how I know that it's an infinite discontinuity. Okay. How about the last one down here, number 4? What type of discontinuity does this graph have? If you think you know it, go ahead and put it in the chat box. Is it a removable discontinuity? Is it a jump discontinuity? Or is it infinite, like the last one? What do you guys think? Of those 3 types of discontinuities, where would the discontinuity be? Where is the location? And what type of discontinuity is it? Go ahead and put it in the chat box if you think you know it. So where is the location of the discontinuity? And what type of discontinuity is it? That's what I want you to figure out for number 4. Yep. I'm getting a whole bunch of answers. You're all right so far. This function is actually continuous. This function is continuous. And the reason why is because it has no discontinuities at all, right? So that was kind of a trick question. But this function is continuous. It's even absolutely continuous. The reason why is because it has no discontinuities. It doesn't have any holes. It doesn't have any jumps. Doesn't have any vertical asymptotes either, right? I could draw this function without picking up my pencil from the paper. So this function y equals x squared, the quadratic function, it is continuous. In fact, it is absolutely continuous. So we can say this has no discontinuities. No discontinuities whatsoever. So there are functions that are going to be continuous. They're not going to have any breaks in the domain or jumps in the y-axis, none of that stuff. Some of them can actually be completely continuous or absolutely continuous. Okay, so those are types of discontinuities that you may see on the homework. Okay, how about number 5 and number 6? Number 5 and number 6. Go ahead and sketch those and see if you can figure out where the locations of the discontinuities would be and what type of discontinuities they would be. Let's start off with number 5. Go ahead and write it down on your paper. What type of discontinuity is there? Is it removable? Is it jump? Or is it infinite? And where is the location of the discontinuity on the x-axis? Where do you guys think the discontinuity is? Go ahead and write that down on your paper. You don't need to type it out and send it to me. Okay, the location is pretty simple. The graph is actually a constant line until you get to this point, and then it jumps all the way down here, and then it keeps on going. So this is a jump discontinuity. This is a jump discontinuity. And where would it be on the x-axis? It would be right here at x equals 1. So it's going to be at x equals positive 1. So right here, that's where the discontinuity is. That's where the disconnect is. So you have a discontinuity right here. So that means I would have to actually pick up my pencil from the paper and move it down here and then keep on drawing the line. Okay. How about number 6? Number 6. You've seen this function before. I guarantee you. What type of discontinuity does it have? Is it removable? Is it jump? Or is it infinite? Or does it have no discontinuities at all? But if it does, what type is it? And where is the location on the x-axis? This is actually the absolute value function, right? So you're graphing y equals absolute value of x, and you get this V shape. And there's no discontinuities here, right? So this function is continuous. In fact, it's absolutely continuous, but you don't need to know that. You need to know that it's continuous, right? It has no discontinuities whatsoever, which is great. That means you can draw the function without lifting your pencil from the paper. Did I spell that right? Discontinuities. Yep. So this function is continuous. It has no discontinuities whatsoever. That's the absolute value function. Now, it does have a sharp corner, right? It has a really sharp corner right here at x equals 0, but that doesn't mean anything for continuity. It's still continuous. What you'll learn in calculus is that at that sharp point right there at the origin, that is a point where the function is not differentiable. But that's another lecture for another time. But this function is definitely continuous. Okay. All right, let's try these two right here. Name the discontinuities and their type, if any. So this is number 7, correct? Number 7 and number 8. So for number 7, what type of discontinuity is it? Is it removable? Is it jump? Or is it infinite? And where is the location of the discontinuity on the x-axis? That's also important. Where is the location of the discontinuity? Go ahead and take a few seconds. Go ahead and write it down. See if you can get it before I get it. Okay. So it tells you how to graph the function at the bottom. It tells you that it's basically a fraction, right? It's got a numerator and a denominator. So this is a rational function. This is a rational function. And we say something is rational if it can be written as a fraction. So the more you know. Okay. Now, it says that this is true only if x cannot be equal to 2, right? But if x equals 2, the function is going to take the value of 1. That's interesting. That's because when you factor the top, you're going to get x minus 2 times x plus 1. On the bottom of the fraction, you have x minus 2, right? So the top and the bottom are going to cancel out. This and this are going to cancel, leaving you with x plus 1 with a discontinuity at the removed factor. So the removed factor was x minus 2. If we set that equal to 0, we'll figure out that x equals 2. That is the location of the discontinuity. So you see how these rational functions kind of cancel out a little bit? This is a removable discontinuity. This is a removable. Why is it removable? Because there's no jumps, right? It's just like if I reached down and I picked up a point from the graph and I put it right here, you know, I just removed the point. So that's the moral of the story. When you have to remove a point, that's called a removable discontinuity. There's no jumps, by the way. And the two ends of the graph do meet at this point, right? So the two ends of the graph are meeting. That's the big difference between removable and jump, okay? When it's a jump discontinuity, it's actually going to jump on the y-axis. You're going to have some y values that are not even being taken up because the graph is going to have a gap in the range. Okay, moving on to number 8. This is a straight line. I can draw this without removing my pencil from the paper. So this is continuous. This is continuous. There are no discontinuities for number 8. But you probably already knew that. Okay. So 4 types of functions that you will see on your homework. There's going to be continuous functions that are really well behaved. There are no discontinuities there. You will also see removable, jump, and infinite. So let's move on to the next slide. Okay. For this one, we're going to state the discontinuities, their locations, and their type. So I circled number 3 right here. And this is from my old calculus textbook, 2011. So what we're going to do with this one is we're going to look at the graph. We're going to study it. We're going to see where the discontinuities are and what their types are, okay? And what we're going to do is we're going to move from the left to the right. We're going to move from the left to the right. So we're going to start at this end over here, and then we're going to make our way all the way over here. So what is the first type of discontinuity that you run into? Well, at -4, notice that we have a hole in the graph. So this is called removable discontinuity, right? And it's going to be at x equals -4. There's a hole in the graph. And if I could fill that up with a point, then it wouldn't be discontinuous anymore, right? It would be continuous at that point. And then what about at -2? That's the next discontinuity we run into, right? What type of discontinuity is this? What type of discontinuity is that? I'm coming in from the left. I stop at this point, and then I jump down to here, and then I keep on going. What type of discontinuity would that be? Would it be removable? Would it be jump? Or would it be infinite? It would be jump, right? So this is a jump discontinuity at x equals -2, because that's the point on the x-axis where the discontinuity occurs. Okay, so then you keep on going with the function from left to right, and there's a sharp corner right here, but it's still continuous right here, right? It's just a sharp corner. And then you go down until you get to x equals 2, and then the graph jumps again, right? The graph jumps again, leaving a gap in the range. So this is going to be another jump discontinuity. Jump at x equals 2. Okay, so the function comes in from the left, it jumps all the way up here, and then it keeps on going. Now, as we move closer and closer to 4, the graph starts to display asymptotic behavior. Did you notice that? The graph starts going crazy down like this. That means that there must be a vertical asymptote somewhere over here. So this is going to be called an infinite discontinuity at x equals 4. X equals 4. Okay. And then the function, keeps on going to the right like this. There's probably well, I don't want to say horizontal asymptote, but the function starts to display horizontal asymptotic action over here because it kind of curls up next to the x-axis, but never crosses it. But we don't really know what the function does beyond this point. We're just kind of guessing. But we do know that there are 4 discontinuities on this graph. There's the removable, where you just pick out a point. There's a jump discontinuity, where the function actually jumps down or jumps up. And then there's the infinite discontinuity, where the graph has a vertical asymptote at x equals 4. So that's very interesting. Good question. Good question from my textbook. I like that. I never thought I'd be using it to teach, though. Okay. And this last question that we're going to do today, for number 4, this is a graph of g of x. We're going to state the intervals on which g is continuous. So what we want to do is we want to state all the discontinuities that you see. We want to state their type, their location, and then at the very end of the question, we want to state all the intervals of continuity. In other words, for what stretches on the x-axis is the function actually continuous? And we're going to answer that question. So coming in from the left, we start off at -4 at this point, and as we come in from the left, we get to here, and we notice that there is a jump. There is definitely a jump. So that's going to be a jump discontinuity, a jump at x equals -2. -2. The graph jumps. And then it keeps on going until you get to x equals 2, and then the graph jumps again. So there's going to be a jump discontinuity at x equals +2. So far, 2 jumps, okay? Does that make sense to you? The jump discontinuities? Okay. And then what's the next type of discontinuity that you see? Well, the function comes in from the left, and it starts going crazy up once you get to 4. And then the function goes crazy down. Okay? That's asymptotic behavior. So that must mean there's a vertical asymptote at x equals 4. So this is an infinite discontinuity at x equals 4. So whenever you have vertical asymptotes, that's when you have those infinite discontinuities. Okay. And then you get to 6. What is 6? There's obviously a jump right here, right? So this is going to be a jump discontinuity at x equals 6. And then what's the last discontinuity going to be once you reach 8? What do you think 8 is going to be? It's kind of hard to tell, but there is a discontinuity at 8. What is it? Is it removable? Is it jump? Or is it infinite at x equals 8? What would this be? Well, we don't really see a jump here, right? We just removed a point. So that would be removable. So you have a removable discontinuity right here at x equals 8. So those are the 3 types of discontinuities that you'll see on the homework. All right, and the last thing I wanted to do was I wanted to state the intervals on which G is continuous. So we're going to answer the question, where is G actually continuous? That's the next question that I want to answer. Where is the function G actually continuous? So if you ever have to pick up your pencil from the paper, you know that it's not going to be continuous there, right? So let's start off from the left. We start here at -4. There's a point right here. And then we keep on going until we get to -2. And then we have to stop because we have to pick up our pencil from the paper right here, right? So the first interval of continuity is from -4 to -2. So here's the way I'm going to write it. I'm going to say x is between -4 and -2. If x is on that interval, then it is continuous, right? And we're going to include -4 within the interval. You could also write it like this, -4, -2, and then close it up with parentheses, because we're not going to include -2 because the function isn't continuous at -2. It is at -4, right? But not at -2. So that's the first interval of continuity. What is the next interval of continuity? It would be between -2 and +2, right? This whole stretch right here. So x could also be between -2 and +2. So we're going to write it like this. We're going to say -2 less than x less than +2. Another way you can write this is the interval from -2 to +2. The function is obviously continuous on that interval. And then what's the next interval of continuity? We start at 2. We start at this point down here, right? And then we follow the function up. We follow the function up until we get to 4. That's where the vertical asymptote is. So from 2 to 4, we also have continuity. I'll say less than 4 because we don't want to include 4. So the way I would write this is square bracket 2, 4, right parentheses. And then there's 2 more intervals that we need to write down. Can you write them down? What are the last 2 remaining intervals? I'll let you do that. And then we'll talk about it. So what are the last 2 intervals of continuity? Go ahead and see if you can write them down. So starting off at 4, the function is going to go crazy down until it kind of stabilizes, right? And then it keeps on going until 6. Then the continuity stops. And then we restart at 6, and then we stop at 8. So what are the last 2 intervals of continuity? From 4 to 6, right? From 4 to 6. So we would write that as 4 less than x less than 6, which would be this interval right here from 4 to 6. And then from 6 to 8. That would be the last interval of continuity. So from 6 to 8, x could be between 6 and 8. And I could write it like this as well. So those are the intervals of continuity. That's where I don't have to pick up my pencil. The function is actually continuous on these intervals. But we are going to have 5 discontinuities in this graph. So very interesting question. So I think I've run out of questions to ask you. So let's just go directly to talking about the homework. Okay, so what's going to be due on Sunday? You're going to have the domain and range classwork, which we did on Monday. Domain and range classwork. We did that on Monday. If you missed that, go back and watch my video. It's on Canvas and YouTube. And today you're going to be trying your hand at the continuity classwork. We're going to be doing that today. Okay. And that's it. Class dismissed. If you still have any questions about the homework, about the lecture, go ahead and stay with me. I'll be trying to answer a lot of those questions. And see you next time. Have a great weekend. Make sure you get your work in by Sunday. And class dismissed. All right, let me hit stop recording.